Yeah. I think you just unplug it. Oakland University. Oakland. How do you like Florida? I'd love to move there.
I believe. I wouldn't. Somewhat. There are a few places, but not many.
Yeah, it's a nice location. Privacy.
Privacy.
Security and privacy, that's why I asked you that question about spamming, and you just...
We are militants against privacy. No, system privacy is open.
Right, well, it's like a lot of things, yeah.
Okay, I'm Annamalai. Actually, conference actually that week's an exam week for us and again, presenting for my students' work. This particular work is in the next paper actually was done by Eidayo Adebola and Biodon Ulanovi. Basically, when they did this part of a cost project, I think one of my colleagues was offering cognitive video costs, and part of the cost project, a couple of cost projects, part of the DRIL program, for master students. So they actually undertake this particular research work. As part of the cost project, turns out from some interesting results, I think suggested them to submit for publication was accepted. So basically, this paper and next paper are somewhat related. Yet they're slightly different. So again, because there's a lot of commonality. Again, obviously, if you look at the paper, you can see the type of detectors that were considered were slightly different. And then, of course, there are two different techniques, mathematical techniques was basically being done. But since they fall under the unifying theme, I basically have combined both the presentations together, so that it's probably much more unified. So I'm presenting both presentations at the same time almost. But again, of course, if you see the papers, you can see subtle differences between them because each one of them uses different mathematical tools to solve the problem at hand. So this is basically what it is. And again, the outline of my presentation, again, basically going to briefly talk about motivation, literature review, summary of a new contribution, overview of classical and improved NH detectors, and then basically look at two general unifying techniques for characterizing performance of generalized energy detectors in moderate or fading environment. So the first approach is using MGF derivative method. Second one is basically trying to use an exponential type integral representation for the generalized Markov function that allows us to essentially even greatly simplify even the characterization even further. So that's kind of even more interesting. And then of course we will essentially apply those tools to characterize performance of both single channel as well as multi-channel or diversity-based energy detectors, and then briefly give a snapshot, a couple of selected numerical results, and perhaps give general lessons that we have learned from this. Of course, the irony of radio spectrum underutilization amidst the scarcity, especially in the lower frequency band, has kind of prompted use of dynamic spectrum access technologies. Of course, trying to find a method to do channel sensing or try to essentially use opportunity dynamic spectrum access, it really requires channel sensing that's quite quick. One of the potential candidates is the energy detector. However, energy detector has its own problems. So basically what I want to do here is that essentially we propose to look at feasibility of using energy detector to solve spectrum sensing problem, but I think we want to essentially look at two important performance metrics. When you look at performance of energy detector or any type of detector, generally there are two important metrics of interest. Not just energy detector, any type of detector. When you try to look in any biological detecting system and so forth, these two particular metrics are always going to become very useful. One is the receiver operating characteristics, which basically plots the detection probability versus the false alarm probability. Sometimes people are also interested in plotting the complementary receiver operating characteristics, which is the misdetection probability versus the false alarm probability. That's just one particular thing. However, when you're using, even though the receiver operating characteristics completely characterizes the performance of any type of detectors, the problem is that if you are trying to compare performance of different type of detectors, it's kind of difficult, especially when the receiver operating curves or the complementary receiver operating curves overlap or crossover, right? So therefore, in the literature, mostly in the biological literature and so forth, people have been started looking into area under the ROC. In fact, more recently, partial area under the ROC matrix. This is again a single figure of the array, allowing you to essentially compare the detectors, different type of detectors in a given environment, and usually the values of the area under the ROC curves lies between 0.5, which indicates poor performance, and much closer to 1 indicates a much better performance. However, having said that, the results on even area under ROC curves are somewhat very limited, and to the best of our knowledge, the only publication that published on this particular topic was an IEEE Council Wireless Communication back about 3 years back, so more than 3 years back. And in fact, even in that particular paper, the author even alluded to the fact that the partial AUC or the partial or marginal AUC incomplete area under the curve is probably even more interesting and more useful, widely used in the genetic gene selection problems and so forth, but becomes mathematically a very intractable problem. So suggested essentially, even for a single channel reception case, the authors proposed to use numerical integration. Again, clearly the method would generally fail when you start looking at more sophisticated, complicated detectors and so forth. So one of the things that we want to essentially look into it is that such a come up with a unifying frameworks, mathematical frameworks that allow us to capture both these general metrics. One, receiver operating characteristics or complementary receiver operating characteristics. Another one is area under the ROC, and in fact, more importantly, complementary or partial area under the ROC. It's interesting that the two frameworks that we're going to talk about will help you to capture both this metric quite elegantly for a wide range of fitting environments. But more importantly, the one based on the exponential type integral representation that we discussed is probably the most elegant and most compact, neat solution, numerically stable to tackle problem head very, very nicely. So that's basically what the focus is going to be. So very briefly, you scan the literature, particularly here we're talking about energy detectors so far, quite a large number of literature that exists. Just want to point out, despite the availability of large number of literature in this particular area, the results are somewhat pretty limited to specific fading environment, mostly relay fading environment, and particularly when there have been some work in 2003 and 2007 and so forth, where they were able to essentially extend that to more practical situations of independent and non-identically distributed relay faded path, as well as in some cases correlated relay faded path as well. So some limited success has actually been done back then, but even until very recently, in 2012, 2011, 2012 articles and so forth, a lot of time people ran into a problem because they're having difficulty in solving some of the integrals that arises in characterizing both the partial AUC, complete AUC, as well as receiver operating characteristics. I'll show you this. In fact, in particular, the receiver operating characteristic performance curves for every shading detector, as well as generalized every shading detector in wide range of generalized practical fading scenarios with independent, non-identically distributed fading statistics or correlated branches and so forth, are generally unavailable in the literature. So that's kind of a problem that the students actually decided to tackle. So basically what the goal was, in fact, what they were successfully able to accomplish was they developed novel moment unity function based approach to unify the performance of such detectors over a wide range of fading environment, including some fading environment like eta mu, kappa mu, alpha mu, which has been proposed quite recently, about a few years ago, by Michel Jacob from Brazil, where he was able to show this particular models are very general, fit experimental data very nicely, and in fact also try to overcome some of the unrealistic existence of homogeneous scattering in a multi-part scattering environment in a traditional model that you have. So they are very known, very general models. Unfortunately, to capture them mathematically, sometimes, especially when you're trying to carry out integration involving the generalized Markov Q function or Nuttall Q function becomes almost intractable problem. In fact, so if someone were to even look at IEEE transaction information theory, just on how to go about efficiently computing generalized Markov Q function alone, there are at least 30 to 40 papers over the past 30, 40, 35 years. Okay, so this again came back from the radar technology, where there's a lot of time when you look at data, you're almost counting photons and everything else, right? So therefore, the distribution basically lends itself to non-central chi-square distribution. You want to find the cumulative distribution function of non-central chi-square distribution, it's basically going to lend itself to Nuttall Q function. And in fact, even Nuttall himself, who used to work in naval laboratory, perhaps, I mean, that's probably the most highly cited report. I mean, he probably published 2 technical reports that can be downloaded from the naval undersea technical reports they produced, which basically provide a summary of all known integrals involving generalized Markov Q function, and all the results that you can probably find in performance and energy detector and everything else have predominantly relied on his results, essentially. So when people have been trying to look at this particular problem and everything, and try to compute the results and everything else, always they try to essentially look for a table of integrals, a known solution to solve the particular integral, and so there have been somewhat quite limited results that exist. But in our hand, we are not necessarily focusing on trying to derive a closed solution, but more importantly, we are really focusing on trying to derive a single integral expression with finite range integral, and that directly helps us to compute them very, very efficiently. That's basically what we really try to set for, and that's what we really want to do. And interestingly, both the frameworks that we're going to talk about here lends themselves to unified expressions for AUC and partial AUC in a similar form to the receiver operating characteristics as well. So it's very, the forms themselves that they lend itself is actually very, very nice. So, and another thing too, because we have 2 particular papers, and these 2 particular students also looked into 2 different types of detectors. One person focused on classical energy detector, another person looked at the improved energy detector. So basically, we want to, again, I want to mention, when you look at classical energy detector, there are different possible implementations you can do in time domain. You can basically pass through a bandpass filter, square the output of the bandpass filter, pass through an integrator, and then that basically becomes your decision statistics that will basically compare against a particular threshold, and you basically decide where the presence or vacancy of a particular spectrum band. In the frequency domain based energy detector, you can implement this using a parallelogram. So you have an FFT, you have a squarer to the sample, and then you can basically compare the output of the sample, square sample, against a particular comparator as well. So obviously in the frequency domain, the estimates that you get from the samples are the power spectral density, whereas in the time domain, the estimates of the sample signal that you're basically going to get are sample energy estimates. So that's basically what it is. And of course, in both in time domain and frequency domain, you can actually come up with improved energy detector. I think in the earlier part today morning, I actually presented a way of improving the classical energy detectors in the time domain. Here I want to basically give you another glimpse of the problem, how you can actually improve the performance of energy detector in the frequency domain. So if you were to look at what's being done, in fact, it's nothing new here. I mean, this concept is generally known for a long time, since around 1970s, where Bartlett and Welch were talking about improving the resolution and sensitivity of energy detection in the frequency domain. So basically what they argue is that instead of essentially trying to perform fine parallelogram to the entire sequence of frequency domain sample sequence of length n, sequence of length n, what they suggest is that first partition the signal, sample waveform that you're basically taking, discrete time signal that you're taking, and then run through parallelogram on the segments itself. So basically what happens is that you tend to be able to get some benefit of statistical averaging, and which can dramatically improve the performance quite rapidly. In fact, on the right hand side, I gave you a very simple illustration of how the segmentation in the frequency domain can be essentially done for Welch parallelogram. Obviously, in the case of Bartlett parallelogram, there's no overlap, whereas in the case of Welch parallelogram, you even allow for additional overlapping between the sample subrecords that you have. So that's kind of provides you additional degree of freedom that might actually can give you some additional improvement as well by reducing the statistical noise that you have in the estimates of the random process. And here, just want to give you a simple illustration here. So, even if you look into the Frequency domain-based LHC detector, and just in this particular case, whether you use Welch parallelogram or Bartlett parallelogram, it's possible to write down the false alarm probability and the detection probability shown at the bottom of the slide there. And so this is basically, the first two equations are basically for the performance in additive white noise channel. So basically, the false alarm probability expressed in terms of incomplete gamma function, whereas the detection probability in additive white noise channel is basically expressed in terms of Markov Q function of order KL, where K partitions with L samples. It's the total number of samples that you are really looking here for the power spectral density estimates K times L. Right? So this is basically what you have, the general form that you have for detection probability. And of course, if you want to go ahead and average, try to find the performance over fading channel, clearly the false alarm probability is independent of the signal noise ratio random variable, whereas the detection probability is a function of gamma, which is the signal noise ratio. So that's exactly the random variable you want to average. And typically trying to average that, again, as I said, really runs into, you normally run into analytical difficulties, mainly because limited number of solutions do exist for solving the integral. I mean, that's only for single channel reception. If you start looking at diverse reception and so forth, the problem becomes even more complicated. Take a very simple example of maximum combining. In a maximum combiner output, what do? You basically try to sum some random variables the output of the combiner. How do you do that? When you try to find the probability density function of some random variables, you have to do convolution operation. So suppose I'm summing L signal from L diversity branches, I have to perform. To find the probability density function, I have to do L minus 1-fold nested convolution integral, which is really mathematically intractable. So what we really want to do is, say, rather than trying to do this in a time domain method, right? So we want to essentially transform that into frequency domain. So therefore, what we want to do is that we want to essentially try to find a suitable form for the Markov Q function representation that lends itself to, that overcomes the difficulty of evaluating the integration directly. So one of the things that we described here is, first of all, we basically use the canonical representation for the Markov Q function, which I have actually briefly illustrated here. So this is one of the functions that we actually have used here. So it's a canonical representation. You have both representation. In fact, we found this particular representation actually converges much more quickly mainly because the incomplete gamma function can be implemented quite efficiently as well. And of course, there are very efficient recursive methods that you can even further speed up with what it is. But even without speeding up the evaluation, and to overcome some of the overflow, underflow problems, even if truncating these about 20 terms, 10 to 20 terms already give you desired accuracy for most practical purposes that you run into. In fact, we normally don't have to go beyond 20 terms to get up to maybe 4 or 5, even sometimes 6-digit accuracy sometimes. So this, even though it looks like infinite series, typically they require only a few number of terms, because the series is rapidly converging. So that's one particular series that we would do. An interesting feature about this particular series is this. When you look at this particular series, you can essentially see the term that is a function of gamma is what? This term. And this is independent of gamma and everything else. So if you look into this, you can basically say, wait a minute, this looks like Laplace derivative property. If I'm integrating this over the probability density function, the resulting expression is going to basically looks like, you can essentially invoke Laplace derivative property, and you can actually express the final answer in terms of moment unity function of the combiner output SNR alone. So that is kind of quite attractive, because if you're trying to look at some of random variables, if you look in a moment unity function or the characteristic function, what happens? You don't have to worry about doing convolution operation. You simply have to worry about looking at the product of the individual moment unity functions or characteristic functions. So this is the nice feature that you really get with this particular approach. Okay, so that's one particular way of doing it. And what we really want to do is that we want to essentially exploit that for our characterization. And the second thing is that there have been some other work actually has talked about moment unity function method as well. So we are presenting two different moment unity function based method. One we call MGF derivative method, because the final resulting expression requires the derivative of the moment unity function. Another one more with the use of the expression type integral, we simply require just the moment unity function alone without even requiring the higher order derivative of the moment unit function. And of course, in the literature, quite recently, Herath and Attapattu actually have also looked at moment unit function method, and we call their method as MGF residue method. I'm going to talk about this as well, why we talk this in terms of MGF residue method. In fact, there are some interesting ideas in that particular paper. Unfortunately, the authors did not necessarily bring to the next step that would dramatically simplify the calculation, and that's exactly what we did. We almost closed the loop to some extent. Eventually, the final expression became very, very attractive and very elegant, that helped us to solve the problem quite elegantly. So that's what we really want to do. Okay, and so I just want to mention about that part. And we have talked about the improved energy reactor already, and I think I was mentioning here. So if you look at the last expression here, you can quickly write down the average detection probability in a different fading environment, and the final result requires only what? The kth order derivative of the moment unit function. If you know the moment unit function, if you can evaluate kth order derivative of the moment unit function, then the problem is almost solved. And of course, nowadays you have the symbolic toolboxes that you have and everything else. This thing is quite tractable already. But I think what we want to do is we want to do even better than that. Okay, so that I think the next things that we want to do will make it much more interesting as well. And in fact, this is just a quick, how do you improve the performance of energy vector in the Ficus domain? I think earlier today I talked about how you can actually improve these the time domain as well. So again, for the sake of brevity, I'll just probably present the two results. Again, the form are quite similar as well. Suppose you have 2V samples, in time domain samples, you can show the false alarm probability is given by this expression here, and the detection probability given by expression here. This is for the classical energy vector. And then if you have the improved energy vector, the difference here, there's a U here, rest of it remains exactly the same thing. Okay. And again, same thing. If you do the MGF derivative method, you can actually write down answers almost in a similar form. Okay, and now we want to talk about the key idea what we're going to talk here. So basically, the first integral that you have here is that by appropriately writing the Markov Q function using a contour integral representation, you can write it in this particular form. So Q with order generalized Markov Q function. In fact, we don't even have to be real. Don't have to be integer. Can even be real in this particular representation. What you basically have is you can write in this particular contour integral form. So the resulting expression basically can, if you look into it, okay. So if you look at my Q function is on, what happens? That A is in the form of square root A gamma, right? So basically, when you have A square root gamma, so interestingly, this exponential term can be written in terms of product of this and product of this, because the argument is in the exponential form. Only the first term is function of gamma itself. So therefore, this particular form itself already lends itself to statistical averaging, and this is exactly what Attapattu, Talambra, Herath all have actually used in their particular work. But however, in order to evaluate this expression in closed form, what do you have to do? You have to apply Cauchy's theorem and essentially evaluate the residues, right, of the resulting integral. So that's exactly what you have done. So therefore, their results are quite restrictive to some specific environment where you can essentially evaluate the residues by invoking Cauchy's theorem, right? So that's the limitation of their particular work. But having said that, the contour integral is known, published by, I think, originally published by John Prakis back in 1965. If you look at some of his papers on MRA, PSK, and in fact, digital communication book, I think in Appendix C, actually have this particular representation where he was trying to come up with a unified expression for partially and differentially encoded MRA modulation scheme. So he basically ran into this particular form, and he actually utilized this to simplify some of the calculations. But again, what we are trying to argue here is that by using the Cauchy's theorem, you can actually evaluate the resulting integral, and that's what other people have done. But what we said is that maybe that's not necessarily very desirable, because it's quite restrictive in the sense of kind of solutions you can get. So what we did is that first of all, we recognize the integral that you have here is actually quite it's analytic except at 2 points, z equals 0 and z equals to 1. Therefore, by Cauchy's theorem, what we can do is that we can actually select the radius of the contour. By right, the contour should be anything radius less than 1. So, but we can actually set the radius equals to 1 and suitably deform the contour tau such that it removes the singularity as z equals to 1. So that's exactly what we have done. So therefore, we have defined a new contour. So particularly in contour tau, right, the outer circle here with radius 1, this is my substitution z equals to x plus j omega, so you can really see the radius is 1. So the corresponding value for the angle theta would be from 2 pi minus epsilon to epsilon. And then for contour tau 1, which we have deformed, this is the corresponding substitution for z and the corresponding value for the angle that you might want to, if you want to convert the contour integral into a polar coordinate format. And in fact, after you have done this, I've clearly mentioned in the paper as well, if you try to take the limit of epsilon, because this is a contour integral, we just want to essentially remove the singularity as 0. So if you have the radius to be epsilon here, right, if you make the radius very, very small, if you're taking the limit close to 0 and evaluating the integral by using variable substitution z equals to x plus j omega, you come up with this nice elegant expression. Again, so what you have here is pretty interesting. You have factor half, and you have this term 1 over 2 pi. This is final integration. You have a real term, and if you look into this is again very, very interesting, because if you look into this, the terms are a function of what? Exponential function of a squared and b squared. And what it means that once you substitute this into the expression that you have earlier, this simply requires what? Simply evaluating the Laplace transform of the PDF, which is what? Moment derivative function. So the final expression can be simply expressed in terms of moment derivative function alone without even requiring the kth order derivative. Kth order derivative for single channel disruption is pretty easy. But when you have product of large number of terms, evaluating kth order derivative itself, even though it can be done using symbolic toolboxes in various mathematical packages and so forth, is cumbersome to write it very analytically, right? Because the reason behind that is that you can see immediately the Leibniz differentiation rule. If you have a product of two terms, you're going to have another two terms and you multiply by another term, so you have to do recursively the product, right? So the number of terms actually grows quite exponentially, which is undesirable, but by using this alternative representation of exponential representation with final range integral we have discussed here, the final answer will be in an extremely elegant form, because you really don't even need the kth order derivative, but simply the moment derivative function of the combined output SNR alone. And that's what we actually have done. So if you look into this, so you substitute that back into the average detector probability, the final answer is actually a very, very nice form. You simply require the moment derivative function, you don't even require the kth order derivative, right? So that's significant improvement. And in fact, this is even much more interesting too, because now as long as you can find the moment derivative function of combined output SNR for different type of combiners in a different generalized fitting environments and so forth, our problem is solved. Okay, so that's basically what we have done. So what we are actually trying to do is that for single channel reception is pretty straightforward. Solutions for the moment derivative function for a wide range of fitting environments are known. So now we want to essentially extend that to maximum measure combiner. So in this particular case, the moment derivative function of the maximum measure combiner output can be shown for the independent but non-identically distributed diversity part. Can be shown that they are simply product of the individual channel MGF. And you substituting back inside our expression here, this is what you get. So if you look into it, there's no computation complexity at all. If you use MGF derivative method, this is going to be quite difficult if you go back, right? Because if you, especially when the L is very large. Here, this is very, very elegant, very clean. There's generally no numerical issues at all evaluating this. Very elegant, very, very efficient to compute them without much difficulty at all. Yet being very, very general, because we do not necessarily impose restriction like what all other research have done. They do not assume restricted to Rayleigh or Nakagami fitting environment. Can be applied to any fitting environment, any generalized fitting environment. Second thing is that we do not even assume all the links, all the diverse branches are independently and identically distributed. They can even come from different families of distribution. So this is quite general in that sense, because if you think about trying to do combination of this non-identical as well as from distribution of different family is almost intractable problem. So this actually solves the problem quite nicely. Same thing. Now, I mean, of course, maximum measure combiner is not practical. You have an uncoherent vector. Why are you using maximum measure combiner? Because it requires a coherent receiver. That's just for benchmark, right? What's the best the energy detector can actually do? But more practical diversity detector for energy detector is what? This is non-coherent or post-action square law combining receiver. So same thing. The output of the combiner statistic can be essentially given by the sum. But what happens is that because of the post-action combining, you can show the false alarm probability no longer V, but L times V. So the false alarm probability actually increases the penalty. So therefore, the receiver operating curve is going to shift upwards, meaning that it's going to have inferior performance. So therefore, in this particular case, you can see the detection probability is going to be exactly the same thing. The only difference is the false alarm probability. compared to maximum combiner, so there's going to be some penalty with square law combining because it's trying to do post-detection combining rather than pre-detection combining. And another practical non-coherent diversity receiver is a square law combining receiver. In this particular case, the false alarm probability and the corresponding detection probability in any cohesion noise channel is given by this. Again, remember here we are essentially assuming the links are independent and non-identically distributed. So if you try to essentially carry out the averaging, you can essentially write it in this particular form as well. Resulting expressions are very, very elegant, very nice, simple, and again, very, very general. And of course, just to give you an illustration, so earlier number I mentioned, the eta kappa, kappa mu, and alpha mu are generalized fading distribution that people have, Mikhail Yakov has actually popularized, which is sure to be much better than the existing classical channel models and everything else. And in fact, the corresponding moment density function for each of these particular channels are defined here. Alpha mu is a little bit more complicated, but if you look at kappa mu and eta mu, they are the simple algebraic forms. Okay, so carrying out and evaluating the integration and everything else do not necessarily pose significant computational complexity and so forth. And just to complement another work as well, remember we also require kth order derivative. I've just simply summarized the result of course the paper. You can see the detailed derivation for different prediction models, specifically the kappa mu, eta mu, and everything else. So the kth order derivative for the common channel models that you have, this is the homogeneous SNR for single channel. This is the kth order derivative. You can see the expression becomes a little bit more complicated. I mean, this is for single channel, right? Or we can essentially apply this for IID selection diversity combiner, right? Square law combiner or exponential combiner will be exactly in this same form as well. But if you see the exponential time integral representation, you really don't have to deal with all these type of things. These are much more computational, right? Computationally involved compared to just using the MGF itself. And of course, the finite range integral, so therefore you can quickly evaluate without much difficulty using any standard numerical integration techniques. Right? As a last bit of example, just to show the versatility of this particular approach, we just try to essentially plot this for different type of detectors, as well as situations where you have dissimilar fading parameters for eta, for mu fading environment, for different values of use and everything. In fact, in the essence, rather than going through every single plot and discussion and everything, what I was trying to say is that we do not, unlike all the existing work that's available in the literature, we do not necessarily impose any restriction at all in terms of what the channel fading parameters could be to essentially able to come up with a prediction of performance of such detectors in practical operating environments. Okay, so the key point here is this: as long as you can write down or you can find a way to evaluate the moment density function and the combiner output SNR, you're fine. And in fact, even though in this particular article we have only generated plots for the maximum combiner, square law combiner, and square law selection, the technique can be directly applied to other diversity combining techniques as well, equal game combining, right? A switch and stay, okay, and so forth. So there are a lot of other diversity systems that people might be interested in looking at. But in those cases as well, in the literature, if you look at some scan from the literature, moment density function for those cases are already known, like switch diversity, switch and stay diversity, moment density function.